Bon, bonjour à tous. Nous avons le plaisir d'accueillir ce matin Frank Hergert from Koblenz University. He's going to talk about organ pipes.
Bonjour, Madame et Monsieur. Good morning, everyone. I'm excited to be here and to talk about this topic in your institute because I know that many of you do research on sounds and acoustics. And I hope I can share some thoughts with you. So you see the outline or the content of my talk, and I want to focus on the following topic. So what is a pipe organ, and how can we distinguish the different families of tone? That will lead me to an empirical model to classify the sounds and to group them into something which I call timbre parameters. And then I will investigate combination of pipes called mixtures, very high pitches together. And I will also show something, what happens when we play very low pitches. With very low, I mean pitch below subcontra C. So we are talking below 33 Hertz. And this will also include the aspect of roughness. And finally, we'll give a short summary. And then, of course, I'm interested in your questions and discussion. So this picture shows a nice example of different ranks of pipes. So here on this picture should be 5 ranks of pipes. You see there are smaller and taller pipes, metal and wooden pipes in the back. And in the organ, you need 1 pipe for each tone. So if you want to play the whole keyboard with 61 keys, 5 octaves, you need 61 pipes. And in this example, I have a wooden pipe here, which sounds like this. It's a wooden pipe. It's called a flute. It has a stopper in it. And a smaller one, I can easily remove the stopper. If I remove it, the pipe is open. It's an open flute. And it's higher. It should be 1 octave in theory. In practice, it is not, because we have to consider the end correction. So the pipe is acoustically a bit longer than it appears. So rank of pipes means we have 61 pipes with the same or with a similar sound, for example, a flute. Then we have individual tone colors. So if we have 10 different ranks, we can make 10 different tone colors in the organ. If we have 100 different ranks, we have 100 tone colors, but this means we have over 6,000 pipes. Pipe voicing is the procedure not to tune the pipe, but to adjust the sound, to make it a flute or a string or kind of trumpet sound. And I assume throughout this talk and in all my investigations that organs who have built with enormous effort, for example, see this picture, this beautiful picture, there's such amount of work in this instrument. And I assume it's not only at the outside of the organ case, it is also done in the interior to make a beautiful sound. So if people have focused to make a good sound, I think we can, when we investigate the sound of individual pipes, learn what is a good sound, what is a bad sound, and what is the principle to refine the sound. So this is the idea. The analysis of sound spectra might unveil some principles. In the best case, we might learn something. What is consonance? What is the recipe to have a sound which we perceive as pleasant? The next slide here shows some examples of pipes. So here you see my wooden flute at the top. There are metal flutes as well. There are pipes which are a bit slimmer, called principals or diapasons, mortar in French. And there are very narrow pipes at the top, at the bottom, string pipes, and at the right side we have reeds, trumpets, or other instruments. And we can group them into different tone families or tone colors. Flute is represented in blue, diapason in green, strings in yellow, and the reed in red and related reeds as well. And you see there is a difference in diameter. And when we listen, you should hear that the sounds are really different. I start with the flute, I go to green, to yellow, and then finally to red. So 4 different tone families. Diapason now. Now the screen. And finally trumpet. So this is a simple classification into 4 families of tone. You can make more families or more groups if you like. So at least 4. If we look into a spectrum, then we could see something like this. I've plotted only the harmonic content of the spectrum. So I've cut everything which is noise or inharmonic. So the harmonics are here. This is the fundamental frequency, the octave. This is the second octave, and so on. So I count the partial number. And then you see the spectrum decreases in generally, and there are 2 slopes typically. One slope is this, second slope is here. And if we have stopped pipes, we see a jump between even and odd harmonics. And this represents an open flute. And in principle, if I use a very simple empirical model to fit this, I can cope with only 7 free parameters to adjust such a spectrum. And this is, of course, pitch dependent. So if I do this for all the pipes across the pitch over 5 octaves, I get something like this. This is showing 1 parameter. This was the slope, the first slope. And then you see the blue line is fit through all these measured slopes. And then at the last octave, the slope is steeper. The reason is this was a trumpet rank, and the pipes change from trumpets to principals in the very top because it's difficult to build trumpets up here. So we get 2 slopes, and P is the pitch category. So pitch 84 is should be C7, I think. So in principle, if I fit every spectrum, I get some values, and then I take the average, to equilibrate some deviations, and I get a very simple model, which is just linear. And if I like, it's piecewise linear in this case, because I have to select the top octave off. If I plot all this, so if I plot the spectra, I know the sound pressure level of each partial, first, second, third, fourth, and so on. And I plot this, and I get a spectrum which looks very regular now because I've smoothed the data already. So I see in the case of the trumpet, the sound pressure level increases first, and then there is a dip approximately at the 5th partial, and then it increases again, and then it decreases. And if we go up in pitch from C0, which is 16 hertz, to C9, then you see the spectra changes, but they change very regular. And here at the last 2 octaves, we have this labial pipes, so these principal pipes. So this is clear that we see a difference in the last 2 octaves. And of course, there was no pipe for C0 because this was an 8-foot rank. So the last 2 bass octaves were just calculated because it's so regular that I can just calculate down from C2 and I can calculate up from C8 to C9. So I extended the range. I have got a kind of artificial model for a trumpet. The parameters, I need 7 parameters. Looks a bit scary at the moment, but it's simple in comparison to other models. I have the sound pressure level at the first partial. I have the first slope. I have the second slope, and some other things. And the first slope, you see, there are two expressions because I have to separate them at pitch 84 because the top octave is different here. This is seen here. I have done this for a lot of ranks. Here on the left is an example for a rank called Salise. This is basically a Geigen diapason. And you see, it's also very regular, and the last three octaves are a bit different. The reason is the pipes become so slim in the top, so you have to make them wider. There is no chance to build them. And so you see this in the spectra. And again, I've extended the range down to C0 and up to C9. So I went up one octave further because it's so clear how to extend the range here. I also looked, after having measured all these different flutes, I looked what could be a typical standard average flute. So the typical open flute, for example, this one, if I pull the stopper, then it's an open flute. And a typical open flute, this would be from metal, could look like this. This would be a model from C0, 16 hertz, up to C10, which is 16,000 hertz around. And the same for an open diapason. This is the typical standard pipe you see in the organ because it stands at the front. From C0 to C10 looks like this. Not much different, but you see the slope in the beginning. This is the difference. Slope at the beginning, the diapason is a bit flat, and then you have the decay, and the flute has the decay immediately. I can also now calculate what is the spectral centroid, which you might call brightness, because it's a good representative of brightness. I've divided the spectral centroid by the fundamental frequency here. So I get a number between 1 and 4 maybe. And so you see for the flute, the brightness or the unitless spectral centroid is approximately at 1.0. As a sine tone would have. Yeah? In the very low pitch, it's a bit above 1, so it's 1.2 maybe. But at the diapason, it's different. The diapason, the centroid is not at 1. It's a bit more to the right. It might be even at 2.5 or 3 at the very low pitch, and then it shifts towards 1. So it's very regular, what we see here. Very regular course. There was a picture published by a famous organ builder in the USA. This is the colored circle. You have seen this already on one of the first slides. And he started with these 4 tone colors, which you can read in every book, but he made a finer distinction. So you see there are some dashed lines and 6 colors in total. So he thought about how to arrange all the tone families in a logical circle. And what I did, I compared my measurements, so the data extractions, with the angle on this color wheel. So we see there is an angle, it's 0 at top, and then we go around 360 degrees. And if I do this, I can plot all my flutes, diapason, and strings. We call this flue ranks, underlined in blue. And you see my flue ranks correlate very well, almost linearly, with a parameter which I call weighted average slope. You have seen that the spectra have a slope. It is maybe flat at the beginning and then steeper at the higher harmonics. And I make a kind of average, but it's not just sum everything, divide by the number. It's a bit more complicated. I have more weight at the lower harmonics and less weight at the higher harmonics. That's the idea. It's a kind of weighted average. And you see the flue ranks correlate very well. I've calculated an R square of 99% or something. This is really good. The reed ranks, which are trumpet or tuba or oboe, they are printed in red symbols. And they correlate also, but not so well to the weighted average slope. They correlate better to the spectral centroid. So the right part of the circle can be ordered with the spectral centroid. After seeing this, I decided to compare all my data at pitch 48, which is C4, I guess, so middle C at the keyboard. And I plotted it on this axis over the unitless spectral centroid, which we could call brightness. And on the vertical axis, I used my weighted average slope parameter. And you see in this diagram, certain ranks group. So I see all the open flutes, which are black, they group. I see all the stopped flutes, here, these ones. If I put the stopper in, they are at a different position. They are these blue crosses. There are chimney flutes somewhere in between, flutes with a stopper, with a bored hole in it, with a bored stopper. Then I see the principals or diapasons in green. I see the strings up here and all the reeds somewhere else. If I add access to these diagrams in words, I would say left-right is something like brightness. On the left, it's less bright. On the right, it's very bright, like a trumpet. And if I add a second axis here, then we could say the slope parameter would be described in organ terms, fluty, down, like a flute, stringy, string quality upwards, or we could also say more general, more fundamental here, less fundamental there. Then it is also valid for reed ranks. Less fundamental would be up there, like we see the kumet, kumhorn, or the clarinet, or these things. So in principle, two parameters suffice to group these ranks, to group the tone colors of the organ, only two parameters. Here I've used the same scale as before, the flue or the same colors. The flutes are always blue in these diagrams. The principal or diapason is green, the string is yellow. And the dotted lines represent the typical course of a string over the frequency. This is the frequency of the spectral centroid. We could say it's kind of brightness. And the string would be on the yellow dotted line, a typical diapason on the green, and a typical flute on the blue dotted line. And what you see here are data of the Salice forefoot. We have seen this already in the spectrum. And you see this rank changes. It comes at low pitch from flute quality, then it develops towards a diapason with a slight string quality, and then at high pitch, because the pipes get so narrow, it goes down towards the flute. If we plot a trumpet, a reed rank, we see it's up there. So it is less fundamental, so it's up in compared to an open diapason. And the top octave, of course, goes here because here we don't have reed pipes anymore, we have flute pipes. So plotting over these two parameters, the weighted slope on the vertical axis and the spectral centroid on the horizontal axis, we can have diagrams where we see how a rank behaves across its tonal compass. If we could do this on site while voicing, we could immediately see if one pipe falls out, because it wouldn't be on this line. It would be somewhere else. And we could see, okay, it is maybe too bright and it is too much on the right, or it is too fundamental and it is too much down. And this is voicing, but without these diagrams, of course. But maybe such diagrams would be helpful. And I want to point out, you don't have to do this model fitting. All what you have to do to calculate this diagram is to measure the sound spectrum. So you need a Fourier transform, which is quick nowadays. You can do this on your mobile phone if you like. And then you take all the sound pressure levels from each harmonic and you calculate these two parameters. So I don't need much more than all the sound pressure levels, relative actually only, of the partials. That's all. Typically, the first 12 partials are enough. I've also done one data evaluation where I used each and every semitone. So you see A sharp, yeah, this is B, this is C, and so on. So each and every semitone. And this rank is a lieblich gedacht, something like these pipes, stopped flute, called lieblich gedacht. And when I do this and plot it in such a diagram, I see, okay, typical diapason would be here, typical open flute would be here, but it's not an open flute, it's a stopped flute, has a stopper in it. And what I've done, I've extracted the model parameters, the 7 parameters for each tone, and then I've refined the model with all pipes simultaneously in the right range, open pipes, and with all pipes in the stopped range for the stopped pipes. And then I get these circles. They are regular again. So what you see at these blue circles is a kind of average model over these tones. And you see a few of them are quite off in this diagram. And you can hear this, but I won't present it today. This is something for Torino in autumn. And this is then the reality. And what I believe is that organ builders want to have this smooth. Yeah, they don't want to have these jumps here. They want to have a smooth progression. One should be also fair and say this, this lieblich gedacht rank, this is from the St. Anne's organ. This is the shortcut STA. This is a recording for the Hauptwerk software. And this rank has been built around 1880 something. So it is more than 130 years old. And I'm not sure how much it was touched. So it might be still quite in original condition. And of course, you would usually, every 20, 30 years, you would revoice it or adjust the voicing. And I'm not certain that that was done. When voicing means, voicing is different from tuning. So in voicing, you might observe that at the slit where the pipe has its mouth, there might be dust. Or maybe there are insects and there are residues. It's not speaking clearly anymore. So the first thing you would clean it, you would put the pipe out, you would clean it, and then you would notice, okay, the slit where the air comes out and is not in the right position anymore. And you would try to adjust it by air. But of course, you could in future possibly also use such a diagram. You don't have to. It's like piano tuning. It might help to have an electronic tuning meter, but you don't have to use it. It's a bit like this discussion. Yeah? You might remember that piano tuners refused to use it at first because they can do it by ear better, but it might be helpful, especially for the low pitch pipes, where it is really difficult to hear. Yeah, and this would be the idea of a timbrometer, an electronic aid for voicing. Yeah, it's different from tuning, but of course you can include tuning. It's very simple then. All what you need is a microphone and a small computer, mobile phone, whatever. Maybe an app on a mobile phone and a good microphone. Yeah, that's quickly done. It's Fourier transform. It's not an issue nowadays. Yeah, next idea. I've told you that I will also speak about very high-pitched pipes. And in organ terms, we talk about a mixture. And I reuse the picture from the beginning because what I showed you, these 5 different ranks of pipes, this is actually a mixture. When you press one key on the keyboard, you play 5 different pipes at the same time. You play one, for example, that one, indicated by 1. The 1 means unison pitch. So a C, for example. Then at the same time, you play a pipe which is indicated at 8, at the octave. Then you play a third pipe at the 12th, it's the interval of a 12th, a fourth pipe at the 15th, which is 2 octaves above, and a fifth pipe at the 17th, which is the major tierce above, a major third above the 2nd octave. And such a rank is usually built from flute pipes, and it sounds like this. What I want to play is a Coney, or maybe I give you the name first. So a Coney, these are 5 flute ranks in pitches 1, 8, 12, 15, and 17th, as shown here. And what you hear now is an example. I have 2 Coneys. So I begin with the first, and then I add the second for the solo voice. You will hear that they are not identical, although they both consist of flute ranks. So first example. This is the reason why it's named cornet. It shall imitate a reed instrument from medieval times, but it's actually only flutes like this. And the second example is a typical mixture, which does not contain tierce, a major third. It's only octaves and quints, and the sound example has the unison with it. So what you hear is 1, 8, 12, 15, and 19. So this is the sound associated with the organ. Yeah, it's quite sharp, and it's a specialty to the organ to have these mixtures. And the question is now, how do we adjust these mixtures? Are there some rules? And there are rules. They have been searching for these rules for hundreds of years, yeah, because the principle to build such mixtures goes back to maybe 1100. And there was a lot of trying how to make it. And when we look into details, we can say a few things. In this diagram, you see the pitch on the horizontal axis and the corresponding frequency. For example, if we press the lowest key on the keyboard, the organ keyboard, it is C2 at 65 Hertz. And if we play a cornet, we play the unison, the 8, the octave, 12, 15, 17th, and you see it is all above or left of the blue line. So what is the blue line? The blue line marks the pitch distance in critical bands. And you see all these cornet compositions are left of the blue line. So we can safely play them without generating roughness. If we were within one critical band distance, we would have roughness. And we could have with the cornet if we went down 1 octave further. On the pedal, we can go and play deeper. And then we would have terrible roughness. And all we could play on the pedal low C is an octave, but not the quint or the 5th interval above. This would already sound very rough and unpleasant. And of course, if we go lower to 16 Hertz, we shouldn't use mixtures. So we see with the cornet, we are safe, basically. If we go higher than the 17th, for example, to the 21st, this is the 7th interval, then we shouldn't go too low. So no, not in the lowest octave, but from 1 octave higher, it is safe. So we can say mixtures, or at least the cornet, does not generate roughness. What could we say also? If we go to other mixtures, like the second sound example, and analyze this, I've analyzed a bunch of 3 dozens of mixtures, which are compiled in an older book. And when I look, and here I've used the equivalent rectangular bin bandwidth. I could have used the critical bandwidth as well, so it's just a factor basically. And if I analyze them in the 2nd and 3rd octave, these are the 2 lower octaves on the keyboard, I see there is no distance lower than 1 ERB. So they are all designed in a way or composed in a way that they do not generate acoustic roughness. If we go to the 4th, 5th, and 6th octaves, it's the same. Now, without exception. If I go to critical bands, then I see, okay, I have a bunch which are a bit lower than 1 critical band because the critical band is a bit narrower compared to the ERB, but this is a matter of definition. But you see the principle. Here in this shaded region, there is nothing. And so we can say, aha, there is a principle. Yeah, avoid acoustic roughness. And of course, you know, this was done long before the science of psychoacoustic has been invented. This was done by try and error. The second sound example, the mixture, would look like this. You go up from lowest pitch on the keyboard, C2, and then you have these tones. While you go up, you have to break back. I mean, you don't have to, but typically you do. This has been invented over the last centuries to break back. The question is why? Why do you break back in pitch? What is the idea behind? And if I look to the cornet in comparison, the cornet does not break back. Start with your 4 or 5 pitches and you go up. That's it. But the mixtures usually break back, as shown in this example. And we can ask, what is the reason behind it? And if I calculate this, the brightness, spectral centroid, of such a mixture of 4 rings, which break back, then the brightness changes. Here it's shown in the green bars. The brightness at the lowest pitch at C2 is 8 point something, expressed in partial number. And at the top C, it's maybe 2.5 or something. So it's lower. Why is this? Acuta is a name for a certain mixture. In organ terms, we have strange names sometimes, yeah. The first graph, we have, this is the keyboard, 5 octaves on the keyboard, and here, these are the pitches sounding. So if I play this special mixture on the lowest key, I would hear a C4, I would hear a C5 and a C6, and I will also hear a G4. So it would play a chord, basically, consisting of octaves and a fifth interval. And when I go up, let's see, for example, at C6, what would it sound there? I would press the key C6 and I would hear C6, C7, C8, and G7. So it's different compared to the lowest key. Yeah, so it breaks back. These are these steps here. They break back. And if we plot the brightness at certain pitches, you see it steps down. And comparing this to my ranks, which I've modeled, then you see this behavior is also seen in the trumpet rank. These are 2 different ones. One is on the great division of the St. Anne's organ. One is at the swell division of the same instrument. And you see this looks very similar. And I think what organ builders aim for and also aimed for in the past is to add a kind of brightness to the organ sound, which is not too dissimilar from a trumpet without having to build a trumpet. Yeah, you generate something. The attack of the pipe is totally different. It doesn't sound, the attack is different, but the in the steady sound, this kind of brightness is similar. So it decreases when you go up in pitch and it increases at low pitch. Very similar to an orchestral trumpet. And maybe it has to do with the fact that in Baroque times, for example, the trumpet was only used at high festive days, in the church here, maybe at Easter, at Christmas, you use the trumpet. And maybe this is a kind of imitation of this festive sound. So let us go to the opposite, to very, very low pitch. So you might know there is a hearing threshold, and at low pitch you don't hear much anymore, so you need very high sound pressures. You might also know that for large pipes you need a lot of wind, and on the right side you see some drawings of the sizes. Here we have a person, and this is at 65 hertz, 8-foot rank. Yeah, this is 2.40 meters approximately. Then it doubles for the first octave down, and it It's 4 times the length if we go to 16 hertz, and it would be 8 times the length at 8 hertz. You need a lot of space, not only a lot of wind, you need a lot of space in the floor and in the height. So it's very expensive to build. And for open pipes, you need these lengths. For stopped pipes, you can reduce it to half the length, but still it's very, very long. And the last here is a typical textbook drawing where you see the blue is the pressure distribution within a pipe. And you see an open pipe at the bottom and a stopped pipe above. Now these are the dimensions. If we now go look how we can produce these low pitches. There are a lot of technical tricks. The left one shows an example. This is a metal pipe, and it has been mitered. Mitered means it has a kink. In this case, it doesn't have only one kink. I think 6 kinks here, 1 full turn to make it shorter in height. So the length is the same, but it's not so high anymore, so you can put it somewhere. This example of Wurlitzer. And the picture next to it, these are very nice wooden pipes. The ones in the very back, they are not mitered. Then there are some with 90-degree angle. And in the front, they have 3 times 60 degrees, gives 180 degrees. So they go down. It's very nicely made. What else can we do? We could, for example, combine a full-length pipe with an open flute, with a stop flute, and hope that there is some virtual pitch, residue pitch. So we play, for example, 60 hertz from this pipe, 40 hertz from this pipe, 60 from this, and we hope to generate 20 hertz as a residue pitch. And here is a construction where we combine a stopped section with an open section. So these were the 2 corresponding pipes. This is called Haskell construction, and it also amplifies the impression of the blue of the stopped pipe, because the 2 spectra overlap, and you have the impression that you have a full-length open 16-foot flute, not a stopped one. Here are also nice examples. When space is a problem, you can use a stopped pipe with a chimney attached. So in the drawing, it's pointing upwards. In the picture, it's pointing down. It is not important. And when you open this chimney, the pipe gets a bit higher because it is on the way to an open pipe. And now you have to control this valve, and then you have 2 pitches on 1 pipe. So you can play C and C sharp, not at the same time, but after each other. Same pipe. And you can employ this. On the left side, you see such a pipe, which has 7 chambers attached to it, all with valves. This is a cross-section. This shows this pressure distribution of sound wave. And what you can do now is that you open valves and attach these chambers. And when you do this, the pitch goes down, 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 down. So you have 8 semitones, if I'm correct, 8 semitones at 1 pipe. So you can play between B0 and E0. And for the last semitones, you would need other pipes. But at least instead of 7 or 8 pipes, you have only 1. But this is an invention from Compton in the UK and is still built today. So it is in such extreme spaces where you have no option, you can do this. This actually, the picture shows such a pipe behind an organ case. So you see the door, the organ is to the left, and this is the back of the organ, and it sits there, and these low frequencies spread through the room. So it's not important where to position this pipe. Other option, you might know this turtle-like thing. This is an ocarina, small flute, based on the principle on a Helmholtz resonator. And if you build this in very large scale, you get, I would say, a contrabass ocarina, which was patented 1925 by Compton. This is the pipe mouth. It looks like a usual wooden pipe, nothing special. But inside, on the other side of the organ case, it looks like this. So it's a large wooden box, and there are tone holes, and there are mechanical fingers. And when you close all these holes, it is a very low pitch. When you open, it's high pitch, like on this small ocarina. There is not much sound on the next file, and you wouldn't hear anything on your computer phones, but the movement is interesting. When this thing is in action, what I'm showing you is playing down from B0 to A sharp 0, playing down, how these fingers move. 2 are closed, 4 are closed, 6. Then you play down. What you hear is the mechanical action, not the tone, because we are playing down to 20 hertz. And here are examples of the fingerings if you want to build such a thing yourself. It's very interesting. And the slit on the top is for tuning. So if you leave a hole open, you can raise the pitch a bit. And it's also louder because there is more sound wave coming out. You could close this, then it's even lower in pitch, but not so loud anymore. Behind at the wall, actually, these are metal chimes. These are not pipes, these are chimes in the organ. This is an example from Belfast, by the way. So what could we say about this low pitch? First, there are many inventions to provide these low pitch, these deep bass tones in pipe organs. There are a lot of inventions. I've shown you just a small selection. We can ask, what is the musical value of these things? What is the value? Why are organ builders doing this? Why are organists asking for this? It's expensive, as you can think. And we can say, okay, the fundamental frequency, this is so low, it is most probably below the hearing threshold because the listeners are not exactly standing next to the bass pipe. When you tune the pipe, you can hear this, but not in the church. When you're 20 meters away, you're too far away. So we are below the hearing threshold, and we also know there is no tonal pitch below 20 hertz or maybe 30 hertz. This is a matter of discussion. What is tonal pitch? So we could say there is no musical value, pitchless tones. On the other hand, we could say the amplitudes of the music in the room is modulated, because when I have a 16 hertz wave somewhere, everything else is modulated by 16 hertz. And this is audible. We call this amplitude modulation, and we know this will give roughness. We are in the range of acoustic roughness. So if we have no pitch or no, let's say no tonal pitch, then at least we generate some roughness. And all this effort to include these special pipes and these large pipes into organs must have some musical effect, I believe, and it can only relate to roughness. And now the question is, does roughness have anything to do with tonal pitch or not? Is it just noise, or has it a relation to tonal pitch? And for this question, I want to show you an example. This is the last part of my talk, where we go even lower in pitch. First, very confusing diagram. On the horizontal axis, we have a carrier frequency. Let's fix it to 1 kilohertz, a sound of 1 kilohertz, typical test tone. If we have a modulation frequency of, let's say, 4 hertz, we know this gives a fluctuation strength. All the green thing is fluctuation. Yeah? If the modulation frequency is, let's say, maybe 100 hertz or 50 hertz, we are in this red region, which we call roughness, and make it clearer by just shading with colors. And if we have the special situation that the frequencies are not too much apart, no, further apart, and a certain frequency ratio, we might get virtual pitch or periodicity pitch. Typically, all this was measured down to 100 hertz. So this is the publication area. In the pipe organ, we know that periodicity pitch is used below. We know, for example, when we have a carrier frequency of 32 hertz, we modulate it with 16, we want to generate 16 hertz. Or if we have 16 hertz modulated with 8, we want to generate 8 hertz. So there is something, this is the reason why I plotted the blue line. It is used. Maybe not down to 10 hertz, but somewhere. There are publications where appears a third form. So there is roughness, there is fluctuation, and probably also R roughness. R refers to the letter R. That's the reason why it's called R roughness. It is described as a coarser kind of roughness. Gröbere Art, coarser roughness. It's perceived as a kind of rattling. And the existence region of this kind of R roughness is shaded in yellow. So it's somewhere between roughness and fluctuation, interestingly. The left diagram refers to 1000 hertz. If we go very low, so I have extended the region. There are no measured data. I have extended what is known. Then we somewhere hit the blue line. And the intersection range between blue and yellow is between 12 and 30 hertz. This is exactly where the organ, the pipe organ, exploits this effect of acoustic bass, of periodicity. The dashed lines refer to publications of Mishkiewicz, who has studied the roughness of pure tones, of sine tones, and also measured roughness perception. And this also fits somewhere into this region. So if we really want to study this low pitch, we can look to an existing instrument. These pictures show a very large building. It was at its time the largest hall without any piles in the middle. So it's the largest free-span roof of the 1930s. This is in Atlantic City at the US coast. And there is an instrument in it, the pipe organ. It's the largest instrument in the world. Unfortunately, in the 40s, there was a large storm and the salt water flooded the hall and the electronics of the organ, or electrics, let's say, so all the wires were in the basement. So everything was flooded with salt water. And since 10 years after its completion, the organ was not playable anymore, at least not in its full size. And it is currently being restored, but it will take years for sure. This instrument has one rank of 64-foot pitch, which means it goes down to 8.2 hertz. So not to confuse, we talk about the minus first octave, C-1 to B-1 between 8 and 15 hertz. They planned to have two ranks. They built one for space region because it's just very, very large. The lowest pipe is 64 foot long. So you can calculate that as 20 meters, something. And it's mitered because there is not 20 meters available. And they have included it that such an instrument has a good fundament, bass fundament. These are pictures. Yeah. So this is a picture from the building times. This is the man who ordered the instrument. He's standing there with the reed tongue. This is, to be precise, a valvular reed. So it's a metal reed with a thick felt plate, and this opens and closes the valve. And this is my own picture. There is a second mechanism driving this thing so that it really speaks without delay. Yeah? So this is a small, this is from a usual 16-foot pipe, and this is 4 times the size, so probably this length. The pipe goes from here up and is in total 60 feet long. It's mitered. And to get an impression, I can play it, but I will play it in double speed. So it is not 8 hertz, what you hear, it will be 16, because otherwise it's useless. You won't hear it, but you can look at the reference given here and then you play it yourself in original speed. I have to go to Yeah. I want to play a bit before. Sorry, I need to go. Just a moment. I see when I want to play from second 50, then I must use this. So does it play now? Oh, sorry. So once again. So let's play from here, because here we have the chance to hear anything. Okay. I don't have to change. Yeah. Okay. I leave it so. Yeah. So what we hear is we play down 2 octaves down, but 1 octave higher. It's double speed. G, F, so D, C, G, F, so this is low C, but we played it in double speed. So it was 1 octave higher. What you hear is 16 hertz. You also, 2 tones are a bit detuned. The reason is it's impossible to tune almost. So if you could record it and then play back, it's much easier. But doing this on site, I think this is a nightmare to do it. And I try to get back to the presentation mode. Yeah. I will try my best. So this is still there, the presentation. And I have to share this once again. So I think this. So should work, I guess. So you should see the screen again. Yeah, okay. So there are 2 organs in the world where we have this kind of pitch, 64, very expensive to build. And it's done with these kind of pipes. Would like to get this green thing off. This thing here. Idea how to get it. Yeah, of course not. So then it's too much technology involved here. Sorry for that. No, that is. Yeah. The green button is good, but where to find it? Okay. I would just. Because you don't have it here. Yeah, I don't see it here. That's the problem. Yeah. Otherwise, I just leave it for the 2 slides here. Yeah. Interesting is to read what an organ builder told, and memorizing this thing. And there is this nice sentence when they tried it out. The 64-foot setup, quite a vibration. When we first played it, a lot of the sound absorbent bricks dropped right out of the ceiling. Not in the chamber, also not in the organ chamber, but out there in the hall. You must imagine the hall is, I think, 40 meters high. So the thing is so loud. It's not only low in pitch, it's loud. So the acoustic energy was so high that these sound absorbent bricks fell out of the ceiling. And they had a lot of problems how to get this done. So you see, it is really designed to make a sound and to be heard, the sound, and it's also heard in the full organ. So it's quite enormous, the thing. And they tried made a lot of attempts to get it right. So they were really focused to give it a kind of musical value. And so the question is, the amplitude modulation at such low frequencies. We know it doesn't possess a tonal pitch. We know there is R roughness. And the R roughness is probably exactly the amount of roughness which we would expect from such a pitch. So if we could hear the tone, the roughness would be the same. And I think the roughness might evoke the same pitch sensation or some kind of pitch sensation of the tone. Of course, not alone, but in combination with the rest of the tones. For example, the overtones. So we might get an impression of the pitch because the roughness is there, the overtones are there, but the fundamental pitch itself is not a tonal pitch anymore. Nice other example, this cube here is for trying out. It's in the state of New York, the US. This is a pipe, as we've seen, such a contrabass ocarina. You can go in, you can close it, and you can make your own pitch, and then you sit in the pipe in infrasound. And while you see this picture, I want to point out that the idea that roughness and pitch perception could be related is not so new. There is a nice publication from the group of Christoph Reuter in Vienna, where it's written, even when the pitch perception is almost impossible, the ear is still able to discriminate the change in timbre. Yeah? It doesn't go as far as saying that we might guess the pitch, but it also mentions the importance of roughness in this context. So let me conclude. First two lines I read because it's covered at the moment. So pipe organs, as you've seen, contain a lot of ranks of pipes. Each rank is voiced for a specific tonal timbre. The ranks of pipes belong to different families of organ tone. Then you've seen I've made up an empirical model, simple model, I would say, to fit the sound spectra of these ranks across the pitch. And I've got two parameters, which I call brightness and the slope parameter, because they describe the tonal timbre and correlate well with the families of organ tone. We could visualize this and use it for voicing. Then we have seen something on mixture stops. They are designed in such a way that they prevent acoustic roughness, but they also add brightness, and this possibly refers to the trumpet. Then you have seen a lot of special pipes for very low bass pitch. For example, mitring, Pascal, and polyphonic pipes to introduce such low pitch in organs where you normally don't have the space for it. And finally, although these low pitch tones are very common in larger organs, you cannot really hear the fundamental pitch. And even if you could, there would be no tonal pitch. So the musical value of it, I think, is related to the roughness. It generates roughness, and this might provoke the pitch sensation, which you usually would have if you really could hear at these low frequencies. And all these examples, I hope, demonstrate that a certain dose of acoustic roughness can be desirable, not just being annoying, but desirable in the musical context. And before I close, I want to thank a lot of people who have taken photographs or the video for this contrabass ocarina. They have written publications. They are themselves organists, editors, scientists. And there is a long list of people who have all contributed in a way so that this work was possible. And the references which I've shown are listed here. So you can make a picture of this slide, and on the second slide, the other references. So thank you for your attention, and I hope there are interesting questions.
I have a question about the tonal wheel. I wasn't sure what exactly it corresponded to. It seems to me that it was a good thing, but then you plotted something against the angle.
Yeah. So the tonal color wheel was developed by Jack Bittards, who is the at Schoenstein Organ Company in the US and is responsible for voicing. And his background is the orchestra, the sounds in the orchestra. And he classified the sounds of different ranks in this color wheel. And this is at first just a qualitative thing. So he has collected 63 different ranks and squeezed into this scheme. So the original picture is much more complicated. I squeezed it down to just colors and a few names. And what I've done then is I have searched the names of my ranks and compared what could possibly be the closest rank in his list and compared it. And when I plot these together, then I see, okay, I get a good correlation for the flu ranks on the left and the reed ranks on the right. And this gave me confidence that these timbre parameters are not totally useless, because someone else who came from a very different approach, from listening to the orchestral instrument, the tone colors in the orchestra, has found this scheme. And if I do a quantitative evaluation, I get something very similar with some regions where I'm not so sure at the moment, but in principle, yes.
My first question about turning this topic, and when you take the sound of the organ, if I heard in terms of cognitive, while the other mixture was in the current. So what do you consider as the reference sound?
Yeah. So the recording of the two cornets, this is a digital instrument, so it has been recorded, but it has been recorded very dry, meaning that the microphone was very close to the pipes, where you normally would not record. But the advantage is you can then transfer this digital instrument in any room, because then you can add your own reverb. And the other recording was done in the church, and therefore there is this natural reverb of the church building in the recording. And what I did to get these data, I used two different instruments, both digitally available as sample sets. One is the St. Anne Church in the UK. This is recorded in the room. And the other is a collection of ranks. Together they are sold as a theater organ, or cinema organ. And all these ranks are recorded very dry, because such instruments are usually found in cinemas and there is not much acoustics. There is not much reverb. And it would be unnatural to have a lot of reverb on the recording. And so part of these ranks was evaluated with almost no reverb, while a part of the other ranks had reverb on it. So this might give small differences in the sound pressure levels, of course, because in one case I have the reflection, in one case I do not have. But I don't believe there is much difference for the shape of the spectra. The flute always looks like decreasing sound pressure levels over a partial number. And the trick is that I plot the partial number on a logarithmic scale, not on a linear scale. And then it's just a falling line.
You also mentioned that probably supporting that the data would be smooth.
Yeah.
That would mean that the idea behind that is that maybe in that kind of topic, something else that I don't know, in the tonality or something. You may find things that are more relevant.
So from what I know, the organ builder and the voicer has an idea how would a low pitch pipe sound like in this rank, and how would a high pitch rank sound like, and you try to regulate it. So you must come from the low pipe over the middle somewhere to the treble, and you tried, as far as I know, to make it a smooth transition, as the examples which I've shown. And here, this special thing is that I measured each semitone in this case. In the other examples, I measured in every fourth only. So I measured the C, the E, G sharp, and then C to reduce the amount of data sets a bit. And here, as I have every single semitone, I see some deviations. Yeah, but I think the aim when you install a new rank, when you voice it at site in the church, then you try to make it as smooth as possible.
Yeah, but that was for example. They had a very smooth transition, and I heard some people think that.
Yeah, that's a good point. We could now say, I try to find the slide, we could say with these parameters, like these ones, with this set, we produce now electronic organ. So we use these functions, which are very simple, and program it and make a perfect organ. I also agree it would sound boring. I think so. I haven't tried it, but I think so. These deviations, these small imperfections, I think this is something which sounds interesting. But on the other hand, I guess there are some ranges which you should not exceed. Otherwise, it's just, it doesn't fit anymore. Some tones, if they are too extreme. So I think when you really want to use this approach to generate something artificial instrument, you should introduce some imperfections as well. To add some detuning is known. Yeah, it helps. Detuning, but this would be a kind of imperfect voicing. Yeah. Yeah, that's true. Yeah, please.
The idea of roughness is then the organ all the time. They know how to control it. Does that make sense?
I'm not sure if I understood the question. So you told the player has the possibility to influence the amount of roughness?
Yeah.
How? Yeah, of course. Yeah. What you can do, that's true, and it's also done when you, for example, draw a very low pitch rank, 32 foot alone, and you play C and C sharp, the lowest two keys on the pedal board, then you get something, yeah, and for the audience, it's not so clear where it comes from, and there is no musical context. You can use this as effect, because then you have these two tones. The difference in frequency is maybe 1 hertz or even less, and you get an amplitude modulation. So what you introduce is a kind of fluctuation strength to the whole sound. Yeah, but above, let's say 10 hertz, I wouldn't call it fluctuation strength anymore. I think then we are in the range of roughness, or maybe R roughness, and then it's something different. And I think this range, which I showed between 30 hertz in maximum and 12 hertz in minimum, this is probably the range where this works. where you really can exploit the effect. Maybe not down to 8 Hertz, but to 12, I think. Half of the minus first octave should work from what I've seen and heard in instruments where the 64-foot rank is provided in an acoustic way, meaning there are no pipes for it, but it's via residue pitch. So you combine the 32 with its fifth interval, and then you can generate some kind of lower frequencies by the difference. And then you have this amplitude modulation. Yes, please.
About roughness, do you make a difference with beats, or is it equivalent for you?
Yeah, the beats or beat frequency is usually used for a few beats per second. Let's say if you say we have 4, 8, 12, in principle, I wouldn't make a difference, because when it comes to detuning, you could also have 20 beats difference, which sounds rough already, whereas 3 beats per second is a nice undulation. And here we are just in the range where we are in between roughness and fluctuation.
Equivalent is agreeable. Very disagreeable for the perception.
Yeah.
But not for always perfectly beaten. It depends on the repertoire.
It depends on the frequency, I think.
Yeah.
If you have 1000 Hertz and you have 1070, then you have a roughness which is not pleasant. If we go down to, let's say, 30 Hertz and have a roughness maybe of 16, half the frequency, 32 and 16. This is the question, yeah, how to name this. This is right, yeah, now I get the thing. It's should we name it beats per second? Is it a beating? Or is it kind of R roughness? Is this better? But I would say fluctuation strength is also not correct, because that is bounded to low frequencies. We are somewhere above fluctuation strength. We are, in principle, I would say, in the range of roughness, but usually people, when you say roughness, attribute it to something at higher frequencies where it really doesn't sound pleasant. And I think at these low frequencies, there is some new thing which occurs. And what is also interesting, when we try to generate a periodicity pitch, if we, for example, use 100 Hertz and 150, then we should get 50 as difference. And it doesn't work very well, to be honest. If we go low in frequency, if we use 50 and 75 to generate 25, it is much better. And something new occurs at these very low, maybe at the lowest 2 octaves. It's different from what happens at above 200 Hertz, for example. And this is applied in organ building. This is used in organ building with this acoustic bass, with this residue pitch. The effect is stronger at very low pitch compared to what you know as Tartini tones or so at higher frequencies. But you have to adjust these two strengths. The acoustic spectra have to match, and I think also the roughness, if we call it roughness, has to match. It has to match what you expect from the residue pitch. If it doesn't match, the effect is poor. If it matches, then the effect is there, I think. But it's difficult to measure. Yeah, as you know, with low frequencies, it's not so easy.
For people on Zoom, some have asked, the recording will be available on YouTube. I will send the link.